Today, we're diving into one of the most, well, dramatic families on the entire periodic table. I'm talking about the halogens. Now, these are elements that are, just incredibly reactive, and they play this massive role in our daily lives, often in ways you probably don't even think about. So, let's get right into it.
Okay, so let me ask you something. What do you think connects the water in your swimming pool, the toothpaste you use every morning, and yeah, even the salt you sprinkle on your fries? It sounds kind of random, right? But believe it or not, the answer is a single, fascinating family of elements.
And yep, that family is the halogens. You'll find them hanging out in group 17 of the periodic table. And let me tell you, these guys are all nonmetals, but they have some of the biggest, most distinctive personalities in all of chemistry. So let's meet the family. We've got fluorine, chlorine, bromine, iodine, and the super rare, kind of mysterious radioactive one, astatine. They range from a pale gas all the way to a dark solid. These 5 make up one of the most intense groups you'll ever meet.
Their name, halogen, pretty much tells you the whole story. It comes from Greek, and it literally means salt former. And that's exactly what they do. It's their core identity, really, this super powerful urge to react with metals and create all kinds of salts. The most famous one, of course, it's got to be sodium teaming up with chlorine to make sodium chloride. Yep, your everyday table salt.
Okay, so if these elements are so incredibly reactive, you might be asking, where do we even find them? Well, it turns out they're kind of hiding in plain sight, all around us. And here's the key thing to understand. You will never just stumble upon a chunk of pure chlorine out in the wild. It's just not going to happen. These elements are, they're just too reactive. They're almost desperate to bond with anything else. So what they do is lock themselves away inside stable compounds. When they do that, they become what we call a halide ion.
And believe me, those compounds are everywhere. We're talking vast salt beds left behind by ancient seas, minerals buried deep in the earth. They're even concentrated in living things. Take sea kelp, for example. It's just packed with iodine. Honestly, the ocean itself is basically a giant soup full of these halide ions.
So this creates a really interesting challenge for chemists, right? If the halogens are always locked up so tightly in these compounds, how in the world do we get them out? How do you, unlock the pure element from the salt?
Well, the secret ingredient is a process called oxidation. Now, to put it simply, it's all about forcing that stable, locked-up ion to give back an electron that it's been holding on to. When you do that, you turn it from a happy, stable ion back into a pure, super-reactive element. But they don't all cooperate equally. Iodide, for example, gives up its extra electron pretty easily. Fluoride, on the other hand, it holds on for dear life, which makes it by far the hardest one to isolate.
Yeah, getting pure fluorine is, it's the ultimate challenge in chemistry. Seriously, it's so wildly reactive that you need an insane amount of electrical current, a process called electrolysis, and you have to run it through a molten mixture of salts. The process works, it produces pure fluorine gas, but the last step is absolutely critical. You have to keep that fluorine gas completely separate from the hydrogen gas that also gets made, because if they mix, boom, they explosively recombine. It is incredibly dangerous work.
Now, making chlorine, that's a whole different story. It's a massive global industry. The famous chloralkali process also uses electrolysis, but this time it's much simpler. You just use a solution of sodium chloride in water. Basically salt water. And this one single process is how we get the huge, immense quantities of chlorine that we use all over the world.
All right, so now we know how to get them out of their compounds. Let's take a look at the distinct personalities of each member of the halogen family, because while they share family traits, believe me, each one is totally unique.
And you can see a really clear trend just by looking at them. At room temperature, you start with fluorine, which is a pale yellow gas, then you move down to chlorine, a greenish-yellow gas. After that, you get to bromine, a deep reddish-brown liquid, and finally, you have iodine, a grayish-black solid that does something amazing when you heat it up. It forms this stunning, deep violet vapor. And guess what? Their reactivity follows that exact same trend. Fluorine is the undisputed champion here. It is the most powerful oxidizing agent known to science, period. It will literally set wood, metals, even water on fire the second it touches them. Then you go all the way to the other end of the spectrum, and you've got iodine. It's kind of the gentle giant of the group. It's the least reactive, and often you need to give it a little nudge with some heat just to get a reaction going. So, all this powerful reactivity we've been talking about, it's not just for making dramatic lab experiments. Nope, it's something we harness every single day in all sorts of applications, from public health all the way to high-tech gadgets.
Let's start at the top with the most reactive of them all, fluorine. Its compounds are essential for modern refrigerants in our ACs and fridges. It's also the key component in Teflon, the stuff that makes your cooking pan ultra slippery and non-stick. And of course, where would we be without fluoride ions? They're added to our water and toothpaste specifically to strengthen our tooth enamel and fight off cavities.
Next up, chlorine. This one is absolutely fundamental to modern industry. That powerful oxidizing ability we talked about, it makes chlorine a perfect bleach for things like paper and cotton cloth. But honestly, its most critical role is probably in public health. It's what we use to kill harmful bacteria in our drinking water and swimming pools. Plus, it's essential for making plastics like those PVC pipes you see everywhere.
And we can't forget the heavier halogens. They have some really vital jobs too. Bromine compounds, for instance, are used to make certain dyes and even some sedatives. And iodine? Well, iodine is absolutely essential for us. Our thyroid gland needs it to work properly, which is exactly why we have iodized salt. It's also a fantastic antiseptic. Think tincture of iodine for cuts. And get this, silver iodide is even used to seed clouds to make it rain.
So when you really step back and look at the halogens, you see this incredible paradox at the heart of chemistry. You have the violent, almost scary reactivity of fluorine on one end, and the life-saving, essential properties of iodine on the other. They are both incredibly destructive and, at the same time, absolutely essential to our modern world. It really makes you think, doesn't it? Where else in our world do we see that same fine line, that delicate balance between the power to create and the power to destroy?